Good morning, students. Welcome to physics session. Today we are going to continue our same lesson, unit 5, motion of system of particles and rigid bodies. In this lesson we are going to see some important concept like power delivered by torque, comparisons of translational and rotational quantities, and introduction about rolling motion. Let me discuss one by one. First we are going to see power delivered by torque. We already know what is power. So power is nothing but potential into current. Here we are going to use the concept of power in related to the torque. Students, here the power is delivered as a work done per unit time. So using the work done, we are going to calculate the power value which will be related to the torque. So I am going to differentiate the expression for the power with respect to the work done of time. So we get the instantaneous power P. What is instantaneous? So instantaneous means at any time we can easily find what is the value of power. So since the instantaneous power is calculated, P is equal to dW by dt. So this is equation number 1. Since we know the work done is equal to tau into dt, that is the work done equal to torque into changing the angle. So I'm going to substitute this value in the above equation. Therefore I get P is equal to tau into d theta by dt. Then since we know what is d theta by dt, that is the angular velocity. Since the angular velocity omega is represented as what? D theta by dt, and replace here. So I get power P is equal to tau into omega. So this is equation number 2. This equation number 2 represents the power delivered by the torque in rotational motion, which means we are studying the power delivered by the torque in rotational motion. Rotational motion means an object is rotate keeping a fixed axis, an object is moving. What about the power value? Similarly, if we are going to represent the power in a translational motion, so P is equal to F into V. What is translational motion? Translational motion is nothing but an object is moving a straight path. That is known as what? Translational motion. Thus equation 3 represents translational motion of power delivered by the torque. Students, next we are going to see a very important 5-mark question. Also the easiest 5-mark question among the comparison related topic. So here we are going to compare the translational and rotational quantities. So again I am telling you, translational means an object is moving a straight path. Rotational means an object is keeping a fixed axis. It will be rotate in a circular path. Now I am going to compare some quantities. What is quantity? We know in the first lesson. So the quantity is going to be compared. What is dd in the translation? How it is represented in rotational. So see the comparison table. Let me discuss some important quantities. So first one, in displacement. So we know the displacement is represented by x, isn't it? In translational the displacement is represented in x, but in rotational motion we have to represent as angular displacement. So angular displacement is represented as theta. Next, time. So in both the translational and rotational, the time is represented by letter t. Then third one, velocity. In translational motion the velocity is represented as change in displacement by time taken, that is v is equal to dx divided by dt. In case of rotational motion, the angular velocity is represented as omega, which will be equal to change in angular displacement by time taken. Therefore omega equal to d theta divided by dt. Fourth one, acceleration. So acceleration is represented by letter A. The definition of acceleration is what? Change in velocity by time taken. Therefore, A is equal to dv divided by dt. In rotational motion, it is represented as angular acceleration. It is denoted by letter alpha. Therefore, alpha is equal to change in angular velocity by time taken. Therefore, alpha is equal to d omega divided by dt. Then fifth one, mass. So in translational motion, the mass is represented as small m. In rotational motion, so the mass is fully changed as what? Moment of inertia. So the moment of inertia is represented by letter capital I, which means mass into distance square is known as moment of inertia. Then sixth one, force. In translational motion, we are calculating what is the force of the object applied to move. Therefore, we know formula F is equal to ma. But in rotational motion, so totally it is different. So we have to represent only the concept called torque, which means the torque is equal to moment of inertia into angular acceleration. Therefore, tau is equal to I into alpha. Then seventh one, linear momentum. So linear momentum means an object moves in a straight path, that is known as linear motion momentum. Therefore, it is represented by P is equal to mass into velocity, or P equal to mv. But in rotational motion, it is represented by angular momentum. So angular momentum is represented by L. It will be equal to moment of inertia into angular velocity. Therefore, L is equal to I omega. Then eighth one, impulse. So impulse is denoted by del P, which means when the force is applied into change in time. Therefore, del P is equal to F into del T. But in rotational motion, the impulse is denoted by angular momentum del L, which will be equal to torque into del T. Therefore, tau del L equal to tau into del T. Then ninth one, work done. To calculate what is the work done by the object, we know the formula W is equal to F into S, that is force into displacement in linear motion. Whereas in rotational motion, the work done W is equal to tau into theta, that is torque into angular displacement. Therefore, W is equal to tau into theta. Then 10th one, kinetic energy in translational motion. So kinetic energy Ke is equal to half mv square, that is mass into velocity square. Then in rotational motion, the kinetic energy is calculated by, so the kinetic energy equal to moment of inertia into angular velocity square. Therefore, Ke is equal to 1 by 2 I omega square. And last one, power calculated in translational motion. So P power is equal to force into velocity. Therefore, P is equal to F into V. In case of rotational motion, the power is calculated P is equal to torque into angular velocity. Therefore, P is equal to tau into omega. So this is very easy 5-mark question, students. So easily you can remember any 10 points. Next, we are going to discuss about third type of motion is rolling motion. So already we discussed about translational motion and rotational motion. So what is rolling motion? Rolling motion is nothing but the combination of both the translational and the rotational motion is known as what? A rolling motion. Now see the definition. The motion of the wheel is a very good example of a rolling of motion, which means keeping a fixed axis, the object will be rolling in a translational motion. Also, some of the examples mentioned here, the round objects like a ring, disc, sphere are also a good example of what? Rolling motion. Now you see the rolling motion elaborately.
Motions possessed by a rigid body. A rigid body possesses different types of motion. For example, translational motion, rotational motion, combination of translational and rotational motion. Translational motion. The motion of the block sliding down an inclined plane is translational motion. All the particles of the body move together. That is, They have the same velocity at any instant of time. Rotational motion. If we fix the rigid body, shown in the above figure, along a straight line, then the body will undergo rotational motion. The examples of rotational motion are motion of a ceiling fan, a potter's wheel, a merry-go-round, etc. In rotation of a rigid body about a fixed axis, every particle of the body moves in a circle, which lies in a plane perpendicular to the axis and has its center on the axis. Rolling motion. Rolling motion is a combination of translation and rotation motion. Let us consider the rolling motion of a circular disc on a level surface. At an instant, the point of contact P0 of the disc with the surface is at rest. If VCM bar is the velocity of center of mass, then the translational velocity of disc is equal to VCM bar, which is parallel to the level surface. Velocity V2 bar of any point P2 of disc is vector sum of VCM bar and VR bar, which is the linear velocity on account of rotation. Magnitude of VR bar is equal to R omega, where omega is angular velocity of rotation of the disc. At point P0 in the figure, the linear velocity VR bar due to rotation directed opposite to the translational velocity VCM bar at P0 is R omega, where R is the radius of the disc. As P0 is instantaneously at rest, therefore VCM bar is equal to R omega. Hence, for the disc to roll without slipping, the essential condition is VCM bar is equal to R omega.
Students, from that video clipping, you may easily understand what is translational motion, what is a rotational motion, and what is rolling motion. Also, you see in rolling motion, you can understand either the translation and the rotational motion. Also, you discuss what is the velocity in the center of mass. Okay, so coming to conclusion of this video. So in this video, we discussed about the power delivered by torque, and a very important 5-mark question, comparison of translational and rotational quantities. Also, we discussed the rolling motion. So we will continue in next video. Thank you.